Excellent. Thank you for the introduction. Just a little bit more about myself. I've been doing this for about a quarter of a century now. I'm much older even than I look. And I've been doing specifically performance work, for example, at the BBC, at Apple. And now I work for Microsoft, of all places. Don't really know how that happened. On the To-Do app, and we were previously Wunderlist. And I've sort of distilled what I've been doing for this ungodly amount of time into a book, which you cannot buy right here, but you can get it on Amazon. And I'm going to try to get you, some of this, some insights that I've poured into that, and in particular some of the larger scale issues that you need to get right. So there's, we all know how to do instruments and get that, fine tuning, but there's some other things that are a bit harder to actually get right. And so the outline of the talk is I'm going to make some general remarks, and then I'm going to give two examples of specifically some architecture issues that can happen. One is I'm going to talk about some implications of the call-return architecture style that we tend to have, and another example of how layering can just really bite you and what you can do about that. So first, some terminology. What do I mean with architecture? It's the large-scale structure of your software systems. I think Martin Fowler once said, all the things that matter. More technically, you're talking about components and connectors. The components are the stuff that do the work, and the connectors tell how well the components connect, how your communication style between the components works. And there are different architectural styles. These are kind of like types for architectures. And particular, the ones I'm going to talk about here is specifically call and return, which is pretty much the default architectural style that we use. We're actually so used to it, I think, that we don't even think about it. Call something, get a result back. But there's others. So for example, pipe and filter. There's event architectures, and many, 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 many more. But wait a second. Aren't we supposed to make it right and then make it fast, right? And God, we've all read this, right? And taken it to heart. Premature optimization is the root of all evil. Knuth said it must be right, and we actually often even just drop the premature, right? Just early optimization, don't do it, and actually optimization is just kind of for dummies. And this is probably the most widely misquoted quote I know of, because there's some context. It's actually, he did write this, but the context was a little bit different. So he's saying, it's not a complete sentence. The start of the sentence is, we should forget about small efficiencies, say about 97% of the time. So only about the small efficiencies, and only 97% of the time, because there's actually the 3% that really matter. And that's the next sentence. Yet we should not pass up our opportunities in that critical 3%. And actually, the entire paper, which is called Structured Programming with Go-To Statements, is really about you should optimize, and I'm going to show you how. And there's a little further back, he says, the conventional wisdom calls for ignoring efficiency in the small, but I believe this is simply an overreaction. In established engineering disciplines, a 12% improvement, 12%, easily obtained, is never considered marginal. And I believe the same viewpoint should prevail in software engineering. So if you get 12% somewhere, Knuth says this is worthwhile. And of course, he said performance in the small, right? And when we're talking about architecture, we're actually talking about performance in the large. And actually, there's a connection in that you have to get your architecture right so that you can actually do the optimization at the end. That's the critical part, and that's really what you want to be doing, right? Because it is true that actually, at the start, you don't know where those bottlenecks are going to be, but you better have structured your code that when you find those bottlenecks, you can do something about them. And Apple found this out when they released Tiger. They were done, except they weren't. And then it took them 6 months to get the performance even just barely acceptable, and then they pushed it out the door. And they never wanted to do that again. And then for the next release, Leopard, they actually had a performance team that was responsible only for the performance of the entire system. And since then, actually pretty much every release has gotten better performance on the same hardware. So that was the general remarks, and now I'm going to talk a little about one example, which is what can happen if you just follow the call return architectural style. What is that? Well, it's really everywhere, right? If you're doing object-oriented programming, you call methods or send messages. If you're doing functional programming, you call functions, right? You call something and it returns a value, and then the function is done. And you can do procedural programming in Pascal, and it's the same thing. And what could possibly be wrong with it? Well, there's subtle problems, and to see those subtle problems, let's look at something very simple. The description method. Right? Every object has it in Cocoa, and it just returns a string that represents the contents of the receiving class. Sounds simple. What could be simpler? Well, this little program. It just does a description of an array, of two arrays, and this is going to crash. It's completely legal. The type checker will say, yep, everything A-OK, and this will crash immediately, right? Because I put the one array inside the other array, and vice versa. And then we have a cycle in our graph, and description goes boom. Okay, well. So description can only handle acyclical graphs. No problem. No. Next program. This is actually worse than the other one, because the other one will crash. This one, if you give it enough rope, will crash your computer. So what happens? Well, first, I put an argument on the command line, so I can say how many of these arrays, and it's just doing array description. That's all it does. And then I get some memory statistics, which we're going to see in a second. And then this is really the trick. Again, I put the new array inside the old array and just keep doing that. So essentially, I have a degenerate tree that just goes down, right? However many times. And that's what happens. So at the x-axis is the depth of the array. So at 50 arrays, we're already up to 700 kilobytes, and the shape of that graph should be familiar. That's a parabola, so we're n squared. And the actual, and you can't really see it because it's hugging the axis so closely. Down here is the actual memory that you would need. The other graph is the temporary memory that's used. So if you go up to 1,000 or 2,000, you're going to start running out of swap space. So why is that? Isn't that, we just messed up our implementation, right? That must be it. No, and the thing is, it's not. It's because the call return architectural style says I must have a complete result, and then I can move on, right? But at each depth of this graph, I need to then have complete result, and then have my temporary result into which I copy the complete result from the previous depth. And so therefore, this is essentially n times m. And since I've made this degenerate graph, which is just a linear, it's n squared. And as long as you're doing call return, you can't really do anything about this. And once you have decided that, well, description works this way in my entire system, and then you discover this, you're kind of stuck. So what can we do about it? Well, we can change the architectural style. Although, of course, since we're in an object-oriented language, we can't just use a pipe and filter directly. That would be the solution. So we're going to write a method that's more pipe and filter-ish, in that it actually doesn't return a result. It's a void, and it gets the argument passed into it. So there is a target, and then we just add to that incrementally. And then we add the opening brace. We iterate over our contents, and then we can do the recursive call. And we don't need to have a temporary complete result. We just have this result that we got actually coming in, and we just add to it. and therefore no allocations. And that looks much nicer. So it's the same two lines, except they just now hug each other really close. And the reason there's a step function is because malloc actually has some bucketing. And you will also notice that the depth now doesn't stop at 50, but starts at 5,000, because otherwise, again, you wouldn't see anything. And it goes to 40,000, and you could just keep going, right? And again, it's not really that, oh, we optimized the implementation. Yes, we did that, but the only reason we could do this because it's a different architectural style. And yeah, that was the other. Well, actually, that is the other graph, but you can't see it. Sorry. So, description. Well, that's not really interesting, right? We don't really want to do that all the time. But so does this actually affect other things? Yes, it does. For example, if you've ever done an XML DOM, that has that same structure as you call it, and then you get a complete graph back. And of course, we don't do XML anymore because we're cool, we do JSON. Well, NSJSON serialization has the same problem. And actually, it's even worse, right? Because you need to give it this whole tree, so you need to convert everything into a temporary representation. And even if and when you come back, you also need to get this temporary representation, which you then do something else with. And the same with NS property list serialization, same problem. Interestingly enough, keyed archiving doesn't have this problem on the architecture side, but they just screwed it up on the implementation because underneath it then uses property list serialization. Which is good because then at least it means you can compatibly change a decent implementation underneath. It's just the existing implementation doesn't do a good job. So again, what was the alternative? Well, we went to a more pipe and filter style. And actually, I'm a huge fan of the Unix pipe and filter pattern. And so instead of just having this very specific accumulator that I just used in this example, what I actually do is I have a whole class hierarchy of these pipes. And one is a description pipe. And then I can actually also solve the initial problem. Because that object, in addition to keeping the accumulator, or actually not accumulating anything and just writing it straight out to standard out or standard error, can keep a track of, oh, I've already seen these objects. Right? And then it can say, oh, I'm in a cycle here. I'm just going to say, OK, cycle, and output this. And you get this incremental accumulation of results. And since this is a very simple interface, you can actually compose these together as well. Architecturally, it's just really, really wonderful. And also, because it has a target and it's not linked to this call return structure, it's great for asynchronous code because you're not expecting a result. You're just expecting the result to be written to the target at some later point. So, for example, in Microsoft To Do, we actually changed the network stack to work with this type of pipe and filter approach. And it's really, really great and got us out of callback hell, which we were deeply in before with Wunderlist. I don't know if anybody's been in callback hell. It's a wonderfully warm place, and you really just want to leave. OK, so the next example is going to be layering. And actually, I was inspired by this by an Objective-C I/O issue 4 on core data, and particularly the article on large data sets. So importing large data sets into core data. And of course, that's by definition kind of a performance talk. And since I was working on a book, I thought, oh, I have an excuse to actually look at this. Wonderful. And that's kind of what's happening there. So you take the public transport data that for example, the BVG here provides in this Google transport feed specification format, which is comma separate values. And you want to have it on your iPhone locally, so the iPhone app could, in theory, give you information without actually having to go to the servers. Great if you're on a subway. And their idea was, well, we're going to have the Mac read this data, convert it into an SQLite database, and then we're going to dump the SQLite database, copy that over to the iPhone app, and then it's available locally. And when I ran it, I was kind of surprised that it took 22 minutes to convert that data. Now, it's 130 megabytes of data, but today that's not really that much. And locally, then, querying that database took about a half a second for a time time and place query, which, that's okay-ish, but not really that great. And so, thinking about it, I noticed that, well, we made some assumptions going in, right? That we're going to do this in layers, right? We have our application model sitting on core data and sitting on SQLite. And, being good architects, all of these are best-of-breed components, right? SQLite is fantastic. Core data has been tuned for, is it a decade now? Yeah, more than a decade. These guys are really smart. And I could not improve any of these components up underneath there. I mean, no way. But somehow that architecture, or something in that architecture, is causing this thing to take 22 minutes. And so I was thinking, well, maybe an alternative would be nice. And one of my favorite architectural styles, which is kind of more of a meta-architecture, is the hexagonal, or I think it's also called ports and adapters. And instead of this strict layering, and we have something external underneath sitting, and we build everything on top of that. The hexagonal architecture says we're going to go inside out. Our application model is primary, what's in memory, what we deal with. And then outside world, if you persist it, or we're going to talk to servers, or you do UI, we do that around that internal architecture. Okay, so let's go with that. First, look at what data do we have, right? So this is some GTFS format files. The first one, so it's obviously comma-separated values, and this is two file types that we're going to deal with. The first is a description of particular stops. So each stop has a stop ID, which is just an integer, a name, and some coordinates, right? Nothing fancy. And fortunately, also, the stop file is just not really that large, so we can just model it pretty much any way we want to. It's not going to really affect our performance. So just do the simple thing, and there we go. So the really large file is, of course, the times, because it records every time any vehicle arrives or particularly leaves a particular stop. That's the big one. That's about the 130 megabytes. Everything else is just noise. And essentially, you have an arrival time, which we don't deal with. We have a departure time and a stop ID. And that's it. So that's the other interesting thing. Very often, the data that you have a lot of tends to be simple. And in this case, that's actually true. So we can model it simply. Now, we just use a struct, a C struct. And actually, we use bit fields, right? Because why would I spend 64 bits modeling an hour? Actually, when iCal did the 64-bit transition, they had that. They had a 64-bit integer for hour, minute, second, day, and it's like, wait a second, guys. You do know that an hour generally, has 60 minutes. That's 6 bits. We don't need more, and you're going to have lots of these, right? It's iCal. There's a lot. You're going to be talking about time a lot. So let's model this, right? 5 bits for the hour, 6 bits for the minute, and our stop index 20 bits. That's enough. That's 1 million stops. We have far fewer than that. And because what we want is to look things up by time, right? That means, that's small integers. We can just sort of index into that, right? And so our search structure is this buckety thing, right? We just say, well, we have 32 hours in the day. Oh, what? Well, they actually extend the day, so when you at midnight, you don't have to wrap around. So they just model it as what we tack a couple of hours on to the day, and that's fine. And that works, because 5 bits. Yeah. And then we have 60 minutes, and we don't do second resolution on these. And then we just have these buckets, and then we have all the stop times, and we just index that array into the stop times. And because the original data doesn't actually come in that format, we actually have to sort it into that format. And of course, we all know sorting is n log n, best case. except when it's not, right? Because we have small integers. Anybody remember small integers? What can we do when we sort small integers? Yes, we can do a bucket sort. And because we have all this in C-struct, we can just allocate those arrays once in one huge allocation. That helps a lot. And then we have to find out how many stops are at each particular location, so we're just counting them. Then as a second pass through that array, we then have to convert those counts into offsets, which is again just adding them up again. And then we do the actual bucket sort, which means we just, when we find a stop with a particular time, we just put the index into that bucket and increment the counter in that bucket. And then actually we do a final step of sorting those buckets so we can search more quickly in them, and that we just use the system merge sort, I think, and that's not really interesting. And so then we have this binary structure, and then we just use fwrite to write it out. Because this is a private communication between these two systems, so we control both endpoints, so why the hell not? And how long does that take? Well, it takes 280 milliseconds compared to 22 minutes. Although the 22 minutes actually included CSV parsing times, which was another 18 seconds, which before weren't noticeable, but compared to 280 milliseconds, it becomes noticeable. So actually, I also spent a little bit of time optimizing that, but I'm not going to go into that because it's not quite as interesting. And so the overall results were actually quite, nice. Using this structure, the time to query went from half a second to 58 microseconds, which is an 8,000 times improvement, which I think is more than 12%. But the time to create is less than a second versus 22 minutes, so that's 1,000x. And the size of the file, although we didn't really optimize for size at all, if I were optimizing for size, I would probably do something different, is also 10 times smaller. So again, we're definitely getting around that 12%, which we think is worthwhile. And this was really low-level optimization, but again, that's not really the core message here, because I was able to do that with the original structure. I couldn't have done any of these optimizations, right? Because all that was fixed by the architecture that I had selected earlier. And again, the interesting thing is, what I had done was really very, very simple. It's not really sophisticated. Whereas all these systems that we're using before are very, very sophisticated. And an afternoon of hacking on any of them would have probably not done anything except prove that I'm not worthy to worship at the feet of the people who wrote that code. But by changing the architectural outlook, I was able to do something very simple that got me, 1,000x. Because focusing on the application model first, and then we add the stuff around. So, suddenly input was just memory mapping, output was an fwrite. And I could add other connectors here, other input-output methods that wouldn't impact what I had done inside the memory model. And that's really the point. And of course, when you're talking about 1,000x performance improvement, that's not a quantitative improvement. That's a qualitative improvement. You can do completely different things than you did before, right? You can leave out steps, right? If you have a compact representation that you can send over the network, you don't need a conversion step. You can do this on the iPhone. If you have servers, you definitely don't need a separate conversion step. They just read the CSV as it comes in at startup and then start serving. Things, and again, if you have 50 microseconds to do a lookup instead of half a second, you can start playing around and add services. Whereas if you're at half a second, with optimization, we got it down to 0.4 seconds and we're super happy. but you're not really changing the game. And that's really what this is about. It's like, if you have high-performance architecture, you can start doing things that you thought were not possible. And that's really sort of the takeaway. Architecture matters a lot. Call return. We're so familiar with it, we don't think about it. Think outside that box, you know. Accumulators work really well. Pipe and filter is an amazing architectural pattern. Hexagonal architecture, think about your model first. Don't think about the technology stack first. Don't say, I'm an architect, therefore, you know, I'm going to do core data, and then I'm going to do this. And no. Think about your model. The architecture will come. And you want to enable those future optimizations. And that's the end of my talk. And you can follow me on Twitter. You can buy the book. Or you can also follow me on my blog. Thank you very much. Are we doing questions? Sure. Yeah.
So we got a few moments for questions. If anybody has a question or two for Marcel. I see somebody over there. Wait for the mic.
There's a mic coming.
Hi. Hi, great talk. Where can we find examples of this pipe filter architecture to see some in work?
Okay, obviously Unix. So that's the canonical example of pipes and filters. Then recently, a lot of the languages have acquired. For example, Java 9 has done in-memory. There's Akka streams. A lot of the reactive, the naming is always odd, is actually very close to pipes and filters, although they don't seem to get much of the performance benefits. So I'm somewhat skeptical there. But yeah, I mean, it's a very long tradition, and again, Unix pipes and filters is a great starting point to look at how that works. And what I did here is really just ask myself, okay, if I did pipes and filters not based on character streams and not on processes, but with objects and messages, what would it look like? And that then turns into the code that I used is in MPW Foundation. That's on GitHub. So I mean. And it's very simple. It's a couple hundred lines of code. Within that larger framework, I should probably just break it out at some point, because it is so incredibly simple. The core is a single method that it says, write object. Well, I'm going to take that object, write it to my target write object. That's 3 to 4 lines of code, and then everything else sort of falls out from that. Fine? It is. Sadly, I don't have any copies here, which is, I know, a complete oversight. But certainly, if somebody has a copy, I'll gladly sign it. And if you're generally in the Berlin area, I'm from Berlin, I'm here. I will also gladly sign your copy, and they're available on the usual places. It's Pearson and Amazon. And I'm not sure whether there are any local copies. Thank you. There's a question in there.
Hello. What was the final result of your sorting algorithm? You said you used fwrite.
Yes.
But the initial problem was referring to SQLite storage. So where did you put the data and how was it queried?
It was in that structure that I showed. Sorry. Builds. It was essentially that structure. What I did not show is, which I mentioned at the beginning, is that the actual stop information is just modeled as plain Objective-C objects. And I don't even remember what I did with them, I have to admit.
Okay, but so structure in memory and all the querying does...
And I just fwrite that structure out. And the reason I can do that is because it contains no pointers. It's just index information, and therefore I can just make a memory dump and write that out. And I can read that back in, or memory map it back in, and it'll be the exact same thing. And since that's not a public, I mean, you wouldn't want to do that for a public file format, and you certainly want to at least add a little header, this is version X of that file. This is version 1 is always identified by it doesn't have a header. Version 2 then has a header. And then you just read that in, and then. But I was just having fun with that, so this is not a production level solution.
Yeah. So just to conclude, the querying is performed when the whole structure is loaded in memory, and it's
memory mapped into memory, and because it's completely again, at that point you don't need to write anything, so we just memory map the structure.
Yeah.
And therefore, the operating system will page in the correct information. And since it's not that much, and so that was, I guess, maybe a follow-up question that I'm going to just ask for you is, doesn't this use much more memory because everything is in memory, right? No, it doesn't, actually. Because the structure is so compact, compared to core data, it actually used slightly less memory. And the other thing is because it's memory mapped and clean memory, it means the operating system can actually throw the resident memory out without any problems. So essentially, the memory pressure of this is very, very low.
Very nice. Thank you.
Thank you. Thank you very much. I guess next step.
Thank you so much.
Thank you.
Really great.